All right, did you guys get a message saying that it's recording? Okay, good. All right, so I'll sort of start over again. So today we're going to talk about sort of the first half of the chapter. Most of the chapter to do with solutions, to do with colligative properties. We'll talk about what that means somewhere in the middle of this section here. So today we're going to talk about osmosis, what that is, how it works, what Van 't Hoff factor means, and a little bit about vapor pressure at the end. Okay, so in your textbook, it talks about, when it starts talking about osmosis, it talks about why it's a bad idea to drink seawater. And you think if you're in the ocean, you got lots of water there, why is it a problem if you drink that water? Why do you essentially dehydrate when you drink what you think, or what actually is water, right? But the problem with seawater is that it has a whole bunch of salt in it. And what that salt does, or what happens when you drink the salt water, is because the salt water has a higher concentration of salt in it than your blood cells do, then basically what happens to your blood cells is that they kind of shrivel up. Okay, and this has got to do with the process of osmosis. So if you have a situation where, let's just say you took your red blood cells or somebody's red blood cells and then just put them in salt water, and if you look at it under the microscope, you would see them shrivel up. So your blood cells are composed, and the outer cell layer is a semi-permeable membrane, which means that only some things can go in and out of the red blood cell. So in this case, we'll just consider water. So water can go in and out of the red blood cell, but the salts, like the sodium chloride, the potassium chloride, and whatever else is in the seawater isn't going to be going through that membrane into your blood cells or out of your blood cells, right? So your blood cells have a certain amount of a certain amount of salt in them. The water around them, if it's seawater, has a certain amount of salt in it. Right. So since there's different concentrations of salt in red blood cells and the ocean water, what happens is that the water inside your cells is forced out of the cells through a process called osmosis. And basically in osmosis, the water is moving from a point of low solute concentration. So again, if you remember what a solute means, that's the thing that is dissolved in the solvent, right? Solvent is a water in this case. Solute would be the salt. Okay, so water moves from a low solute concentration to a high solute concentration. So basically, the water is trying to dilute the salt of the seawater so that it ends up being the same concentration as the salt in your red blood cells. So that's how dehydration happens when you drink salt water, right? Because it has a high concentration of salt, it's just drawing water out of your blood cells and any other cells that it comes in contact with. Okay, cells dehydrate, shrivel, and die, and then you end up suffering as well. Okay, so we'll talk about a little bit more about that semi-permeable membrane and sort of what osmotic pressure is. So how that the solution moves across the membrane and when it stops, because it's not going to move forever, right? The water will move from, say, the red blood cell to the outer seawater to a point, and then at some point it'll stop, and that's due to what's called osmotic pressure. And then, so this is a spontaneous process. It doesn't require any energy to put into it. Okay, we'll talk more about what spontaneous processes are when we get to the next chapter, chapter 12. But basically it just means a process where you don't have to put any energy in. You just put some reactants together and then something happens. So in this case, you just put red blood cells in water, seawater, and the water moves out of the red blood cells. Okay, so it looks like at the bottom here, it describes osmosis sort of the opposite way that I did. So I said it moves from a low solute concentration to a high solute concentration, which is the same as what it says at the bottom, right? Moving from a from a high concentration of water to a low concentration of water. Okay, it means the same thing. Okay, so this is just what it looks like if you have red blood cells and you put them in different concentrations of a salt solution. So if we have a situation where we just described, we are here. Okay, so we have the red blood cells that were put into seawater or water with a high concentration of salt. And then what you can see if I zoom in here a little bit is that here's your red blood cells. And then the arrows are showing the water being released from the red blood cells so that they are shriveling up. Okay, so I got a question just to confirm: spontaneous migration takes no energy because it relies on osmosis, which only relies on diffusion. Spontaneous just means that it'll happen. You don't have to put work into it. You can stop the definition kind of right there. And osmosis is a spontaneous process. Diffusion, it's not quite the right word. Because diffusion itself is a slower process. There's no pressure involved in diffusion. There's no real force involved. It's just something. It's also a spontaneous process, of course, but it doesn't happen quite as. It's probably not the right word, but it wouldn't happen necessarily quite as quickly as osmosis would. Osmosis is more of a process where there's more pressure for the process to happen than diffusion, if that makes sense. I hope it does. If it doesn't, let me know. But you can just think of a spontaneous process as one that happens without putting work into it. So for example, I guess a decent example is a battery, which we will talk about the last chapter in this class. So if you think of a battery, when you have it in your phone, your battery you don't have to do anything to that battery. It is releasing energy to make your phone work or to make something else go. But if you want to recharge that battery, you have to put energy into it to recharge it. So recharging is a non-spontaneous process because you're putting energy in. The release of energy from the battery is a spontaneous process because all you got to do is hook up 2 wires to it, and then the electricity will just flow. Okay, so it's not a perfect analogy to osmosis, but hopefully it gives you an idea of what spontaneous means. Okay, so if we have what's called that, so we're over here. Hypertonic solution would be the one which we were talking about with the seawater. Okay, so that means there's a high. Oh shoot, I need to make that a little bit smaller. So in the outer water solution, this is going to be a high concentration of salt. And then inside the cell would be low concentration of salt. If we have what's called an isotonic solution, then we have the salt is equal both in here and out there, right? So there's water moving back and forth between the blood cells, both in and out at the same rate. So there is no net increase in volume or decrease in volume of the red blood cells. And then if we have a hypotonic solution, we would have low salt here, and then inside high salt concentration. So high salt will be inside, right? So again, we're looking at where water flows. If we have high salt concentration inside the cell compared to what's outside the cell, then the water is going to want to move into the cell, into the red blood cell, and try to dilute the salt concentration so it's equal both on the inside and the outside. So basically both processes, both the hypertonic and hypotonic, are trying to get to this situation here. They're trying to get to the middle where we have equal concentrations of salt on both sides of the membrane. And again, we're saying that the membranes that we're going to be talking about, semi-permeable, meaning that only the water can flow through it, the salts can't. Okay, so the salts will stay where they are. Only the water can flow in and out of the cell or on either side of a semi-permeable membrane. All right, are there any questions? I think I see, hold on. Yep, I see a hand. Go ahead.
I just had a quick question. So in the slides, it says water moves from a high concentration of water to a lower concentration. So if you go back to the cells.
Yep.
So if there's a higher concentration outside for the hypertonic and lower concentration inside, wouldn't the arrows be opposite?
Okay, so I guess I'm talking about it the opposite way. So if you look at the other slide too, it says right here, low solute. So I'm talking about it with respect to the solute or the salt concentration. But I can reverse what I was saying here. So if you want to talk about the concentration of water, so if it's low salt, let me see. Okay, so we have hypertonic. So we have, in this case, we have low water here, and then high water inside the cell. Hold on, is that right? Yes. Oh, are you talking about this one? Hold on, this is, well, that's right. Okay. And then the other one, let's see, this would be, oh, did I make a mistake on this one? Is that what you're trying to say?
I mean, I'm just trying to understand it. So if there's a more salt concentration outside of the cell, wouldn't the water be going into the cell to balance out?
Okay, let's just start at this one. So if water is flowing out of the cell, it's just easier for me to talk about it with low solute because that's the way I learned it. Okay, water moves from high concentrations of water to low concentrations of water. All right. So in this one, so I'm looking at the one here. If water is flowing out of the cell, then that must mean that there is a higher salt concentration on the outside. So it must be a lower water concentration on the outside, high water concentration on the inside. Okay, so the water is moving from, let me go back again, make sure I'm right. Moving from high concentration to low concentration. Okay. So in this case, if we have high water in the middle of the cell, then it has to move out to a lower water concentration. And if the lower water concentration is on the outside, that also means same thing. It means high salt. All right, does that make sense?
Okay, so the cell has a higher salt concentration, whereas the water surrounding it does not, so it would go out of the cell.
Okay, so the in this case, in comparison, okay, so I wrote them both down here. So in the cell, there's a high water concentration and a low salt concentration compared to what's outside the cell. Okay, outside the cell, low water concentration, high salt concentration. So the water is going to move out of the cell from high water to low water, or from low solute to high solute. Okay, so basically it's trying, so the water inside the cell, it's at a lower concentration. The only thing that can move in and out of these cells is water. And since it wants to try and get to a situation of an isotonic solution where we have equal concentrations of salt both in and outside the cell, since only water can move, then the water has to move to a place where it will dilute a salt concentration, right? If the salt can't get inside the cell, there's no way to make the salt more concentrated in the cell so it can match the high salt concentration on the outside of the cell. So the water has to move out of the cell to dilute all the water that's around it so that it can move towards a situation where we have equal concentrations of salt both inside and outside.
Okay.
That makes sense?
Yeah, I think I get it now. So okay. Basically, because there's a higher salt concentration outside, the cell is trying to balance it out by releasing water.
That's right. Right. So it's trying to dilute it so to make the concentrations equal if it can, right? Ideally, it gets to this middle situation here. Well, ideally, it is that situation, but in the process of going there, the hypertonic state ends up shriveling those cells up because they have to lose water.
Okay, gotcha.
Okay, and let's just make sure I have this side right here. So I have high salt. Yeah, I have high salt on the inside, low salt on the outside. So that must mean high water concentration here and then low water here. Right, so again, if we have low salt concentration on the outside and high water concentration, since only water can move, it has to move inside the blood cell to dilute the concentration of salt. And then in this case, that results in expanding the cell. And if it expands too much, the cell could rupture. All right, does that make sense now?
Yep.
Okay, good. All right, so let me see here. So something like a charged ion can't flow through the cell. Yeah, that's right. So we're just saying that only water can flow in and out of the cell. So that's what a semi-permeable membrane means, at least in terms of what we're going to be talking about with osmosis. So water is the only exception to this. It can go through the cell membrane. That's right. So it's the only thing that can move. Anything else, unless it says in the question otherwise, if the question says something like, sodium ions can move through or something, because that's a possibility. But right now we're just considering only water can flow through the membrane, whether it's the membrane of a cell or, as we'll see, maybe it might be the next slide, just a straight membrane, almost like a filter, but it's one that can only let water through and nothing else. All right, maybe it's not quite the next slide. Not quite. Okay, so we have talked about what osmosis is, movement of solvent, again, solvent being water in this case, through the semi-permeable membrane, region of low to high solute concentrations. And so now let's just talk about this thing called osmotic pressure. And this is just showing you the definition and the equation here. So osmotic pressure is just, so if you go back to the previous slide and maybe this situation here, the hypotonic case, there's obviously some, if that cell ends up bursting, there must be some pressure being exerted to force that water in, right? So there's some pressure being exerted, and at some point, if that cell explodes, then obviously there's too much pressure that occurred in that situation. So the pressure required to halt the flow is called the osmotic pressure, because it won't flow forever. If there was a small change, a small difference in a concentration, solvent is water, yes, that's correct. If there was just a small change or small difference in the concentrations of salt between the blood cell and the surrounding solution, then not a lot of water would move, whatever way it's going to move into or out of the cell. So there would be less osmotic, or a lower osmotic pressure, because there's less of a difference in the concentration. The greater the difference in concentration between either side of that semi-permeable membrane, the greater the osmotic pressure will be. Okay, so osmotic pressure is this guy here. There's pi. We'll talk about I here a little bit later. I just put it there because it is part of the equation, but initially your textbook doesn't talk about it. Right now, we're just going to assume I is 1, and a little bit later in this section, we'll see what circumstances make I something other than 1. Okay, M is the molarity. R is the universal gas constant, which is 0.08206 liter atmospheres per mole Kelvin. And if that is our constant, that's telling us, I think I said it in this class, it's either this class or Chem 283. I always get mixed up because I say the same types of things in each class sometimes. So here's our constant. That's going to tell us what units we need for everything else. Right, so we know molarity should be moles per liter, and then we have moles per liter, or liters and moles in our constant. Osmotic pressure, in this case, we have it in atmospheres because we're using our constant that has atmospheres. And then the temperature, T here, has to be in Kelvin because our constant has Kelvin. Okay, if our units of the other terms, the M and the T and the pi, they don't match our constant, then that's not going to give us the correct units in the end. Okay, I doesn't have any units associated with it. It's just a number. Okay, and as I was saying at the very beginning, this, we're going to be talking about colligative properties, and this is the first one. What does T stand for? T is temperature in Kelvin. Okay, so a colligative property just means that it is a solution property that depends on concentration of the solute particles. Another way to say that it depends on the number of solute particles. So again, solute being sodium chloride or calcium chloride or some kind of salt. And not the identity. So it doesn't matter that it's calcium or sodium or potassium. It just matters how many particles are actually in the solution. All right, so question. So a greater difference in concentration on either side of the cell results in a greater osmotic pressure. Yes, that is correct. Or was it a difference in change that increases the osmotic pressure? It's a difference in concentration. So if there's a low salt concentration inside the cell and a high salt concentration outside, then you are, sorry, I'm trying to read questions at the same time here. I'm getting myself mixed up. Which variable is the constant? R, yes. Thank you. All right, let me get back up to the other question here. So greater difference in concentration on either side of the cell results in a greater osmotic pressure. That's correct. Or was it a difference in change that increases the osmotic pressure? I'm not sure what the second half of that question means. It seems like it says the same thing as the first one. Oh, charge. Okay, a difference in charge. Now the charge doesn't, if we're just talking about concentration, I'm not worried about any kind of charge. We will talk about how, I won't say it's really charge that affects things because it is number, it's number of solute particles. So for example, if you have sodium and chloride, you know what, I'll just talk about that later once I get there. But charge doesn't matter. All right, good. All right, any other questions? Okay. All right, so here's just another way to look at osmosis, and just some other definitions again, just sort of explaining what osmosis is on the left there, and you know, some of the things I've already said. So I don't think I want to repeat what's on the slide there. You can look at it if you want. So I'll just zoom in on this little apparatus here. So if we have a situation where we have, right, we have our semi-permeable membrane again, which is right there. It's separating two different solutions. So one that's normal saline. So in this case, it would have a higher concentration of water than the seawater does. And the reason I know that is because the arrow right here is showing me which way the solution is going. So remember, it goes from a high water concentration to a low water concentration. Or if you want to think of it, it goes from low solute to high solute concentration, right? So the seawater has to have more salt in it because the water is moving across that membrane from the right side to the left side. Right? And if you want to look at it in terms of how that's happening, okay, so these arrows here are showing that the water is not just moving in one direction. And you sort of have to consider that's happening. It doesn't mean that water only moves in one direction across that membrane, because it can move both ways, but the overall direction is from one side to the other, right? So as the concentration gets more equal, those blue arrows will change into, you know, some of those blue arrows will change into red arrows. So we get to a situation where we have the same number of water molecules going right to left than there are going left to right. Okay, so at this point here, we have more going right to left. So that means there's a net pressure going to the left side, or a net movement of solvent to the left-hand side. Okay, and then as that continues to happen, right, we end up with a situation where we have more solution on the seawater side than we do on the saline side or the saltwater side. And that difference is what is referred to as the osmotic pressure. So that difference will be greater if the difference in concentration of solute is greater on each side of that semi-permeable membrane, right? So a small difference in concentration of solute will result in a small osmotic pressure. So maybe you'd have something, maybe the seawater would end up there, for example, if it was a more equal concentration. If it was a greater concentration, then maybe this U thing, this apparatus, it overflows. Okay, but at some point, the concentrations of solute will become equal, And then we have a situation where it's showing a balance of flow. So the flow is going equally left and right. So there's no net increase or decrease of water on either side, right? So basically what it's saying is that each of these two levels, that level won't move, that level won't move, okay, because the water is moving back and forth equally. Okay, if you want to look at that up here, you can see that there are an equal number of red and blue arrows. Okay. Now, I would say I think this is not a good depiction of it because I'm looking at it now. If you're considering these guys here as salt ions, so this is probably sodium, that's probably chloride because that's usually how those guys are colored. But this should probably show equal amounts of salt on both sides of that membrane, right? So this is still showing this situation over here where we have more salt on the left, which means the water's got to go this way to dilute it. But once it's diluted, then we really should have the same amount of the same concentration of salt on each side. So it's maybe a little bit misleading with this picture, but it should have equal concentrations on both sides. Otherwise, there will be some pressure for the movement of water somewhere. All right, the next slide is a practice calculation. So does anybody have any questions before we move there? Okay. All right, so this next couple questions, I think I have 2 slides with questions. Yep. All right, so this one shouldn't be that difficult. So container divided by a membrane, permeable only to water. On the left side is a solution of 0.1 molar sodium chloride, and the right side is a solution of 0.2 molar sodium chloride. What flows where? So I'm basically asking, if we were to draw this out, that's probably an easy way to do it. So let's just draw this out first. Something very simple diagram. So you can do make a little box and then put your semi-permeable membrane in the middle somewhere. And then we would have what we have 0.1 molar on the left. Come on, where are you? There we go. And then 0.2 molar sodium chloride over here. Okay, so the question is asking you what flows where. So the possibilities of things that can flow are water, sodium, and chloride. So if anybody wants to put in the chat which of those 3 things is going to move, or if you just want to yell it out, let me know. Water is going to move. It says in the question, water is going to move. I think, doesn't it? Well, it doesn't really say, but since the membrane is only permeable to water, then that's the only thing that can move. The water is going to flow towards the 0.2 molar. That's what somebody said in the chat here. And that would be correct because, again, we have, since only the water can move, the only way to make these 2 concentrations on either side equal is if the water would move, right, from right to left. Right, so eventually, maybe the little U diagram on the previous slide is probably a bit better for showing what would happen, because obviously the left-hand side is going to fill up a little bit more with water. So it's probably not a good idea to show a closed loop here or a closed container. But you can at least see where water is going, I hope. All right, does that make sense to everybody? If not, let me know. Okay, so the next question, a container divided by a membrane permeable only to water. Each side of the membrane is filled with an equal volume of a salt solution. If the water flows from left to right, which of the following statements is true? So stick your answers in the chat. If you want, you can draw a little diagram also. So I have an answer of A. All right, so far everybody's saying A. All right, so A is right. Okay, the solution on the right is initially more concentrated. So if you wanted to draw a little diagram, we'll just, here's our So we'll put a semi-permeable membrane just right here. And then on, let's see, it says each side of the membrane is filled with an equal volume of salt. If the water flows from left to right, so the water is going this way across that membrane, which is true. So if we know it goes from low solute to high solute, then this has to have high salt here on this side. This has to have low salt. And the solution on the right is initially more concentrated, right? That's what has to happen. All right, cool. All right, so here's a quick calculation using the osmotic pressure formula. So if the total concentration of solute particles in the fluid inside a red blood cell is 0.310 molar, what is the osmotic pressure of this fluid at body temperature, which is 37 degrees Celsius? And the membrane surrounding the cell is semi-permeable, and we're always going to assume that semi-permeable means only permeable to water unless it's specifically said otherwise. Okay, so for this question, we know our equation is going to be this, right? And we haven't talked about I yet, so we're still going to assume that is 1. I don't see anything. Internet horrible. Sorry. I am recording it, so you can check this out later if you can. I am on slide 8 of the slides. So if you just want to follow along there, you can do that. And hopefully what I'm saying here is going to help you know what I'm writing on each of the slides. Sound good? Okay, so we have pi equals IMRT. And since we haven't talked about I yet, we're still going to assume it's 1. And then we have M is molarity, R is the universal gas constant, T is the temperature. So we're given the concentration. We're trying to find, what is that? We're trying to find pi, right? So we're going to have pi equals, we'll just call this 1 for I. The molarity is 0.310. R, so I'll put a unit there just to make it more clear. Right, R is universal gas constant. Liter atmospheres per mole Kelvin. Right, and then since our constant is telling us we need Kelvin temperature, we're going to have to turn 37 degrees into Kelvin, right? So that's going to be 37 plus 273, right? So it's going to be 37 plus 273, right? That's going to be Kelvin. And then if we solve for osmotic pressure, then we are going to get, oh, where am I at? 7.89 atmospheres. Okay, so if you look at that number, 7.89 atmospheres, that is pretty high pressure, right? So we experience right now 1 atmosphere of pressure. That's how much atmosphere is pushing down on us. So 7 atmospheres is quite a bit more pressure than that. So depending on whether or not the, let's see, which way would it be going? I'm not sure. We don't know the concentrations of everything everywhere, but assuming this is going inside the cell, I'm not sure a cell can withstand 8 atmospheres of pressure. So that's probably going to be exploding that cell. Right, does this make sense, everybody? And I'm assuming any kind of radio silence means yes.
Oh, why would the cell be exploding here?
I'm just not sure where, I'm not sure where the salt, the higher salt concentration is, because I don't know what the concentration is. It doesn't say which way the solute is going. It's just saying what is the osmotic pressure. So I mean, you can assume either way. If it's going into the cell, it'll probably explode. If it's going outside the cell, then the cell is going to be shriveled. Yeah, we just don't know which way it's going. That's all.
I just got a quick question.
Yep.
Do you know where you got the 273 from?
That's okay. So 273 is the same as 0 degrees Celsius. So whenever you're turning turning degrees Celsius into Kelvin, you have to add 273 to it.
Oh, okay. So that's just the conversion, but you left it the way it is.
Yeah.
So you
Yeah.
Okay. All right.
Yeah. So it'd be like what, 310, right?
Yeah.
310 if you wanted to call it just Kelvin, but 273 is the conversion from degrees Celsius to Kelvin.
Oh, all right.
Mhm. Okay. All right, so now we can talk about what I is in this equation. So I is called the Van't Hoff factor. And basically what it has to do is, remember we're talking about colligative properties, what it means how many, it means it matters how many solute particles are in the solution. So if we have something like sugar, sugar is, if you remember, is something that's not ionic. So ionic is something that would break up in solution like sodium chloride. So something that's non-ionic like sugar, it's not going to break up in solution. So when it dissolves in water, it's still just going to be a sugar molecule. Right? So one sugar molecule as a solid, one sugar molecule as it's dissolved. So the problem that we come across, not a problem, but the difference with something that is ionic, like sodium chloride, is that sodium chloride is going to break up, right? So we could have sodium chloride as a solid, is an ionic solid, but when it dissolves in solution, we get an Na plus and a chloride minus, right? So if we had 1 mole of sodium chloride and we dissolve that in water, we now have 1 mole of sodium and 1 mole of chloride. So you can see we have twice the number of molecules, right? Initially we had just 1 sodium chloride molecule. Now we have 2 ions, sodium ion and a chloride ion. So the Van't Hoff factor takes into account the breaking up of ionic molecules. So in the case of sodium chloride, the Van't Hoff factor I is going to be 2 because there are now 2 ions in solution rather than just 1 sodium chloride, staying together as an ion. If we had something like calcium chloride, what do you think the Van't Hoff factor for calcium chloride would be? Anybody have any guesses?
3.
3, because we have a calcium 2 plus and 2 chloride minuses, right? So that for calcium chloride, it would be 3. And for like potassium chloride, it would also be 2 because I have a potassium plus and a chloride minus. Okay, so under theoretical conditions, if you want to call it that way, sodium chloride is going to have an Van't Hoff factor of 2, but the concentration of sodium chloride matters a little bit as well. So what happens if we have a low concentration of sodium chloride? So this is just showing basically this solution up here is a sodium chloride solution at its freezing point. Okay, so those little blocks up there are supposed to be ice. So it's supposed to be at, if it was just water, it would be 0 degrees Celsius. But as we'll learn a little bit later, having a solute like sodium chloride in water modifies what the actual freezing point of water is. So if we have a low concentration of sodium chloride, in this case, we're saying it's 0.01 molar, there's a lot of space in between all the ions, and they're sort of, surrounded by waters, and they're all separate. So in that case, we truly do have each 1 sodium chloride molecule does break up nice and neatly into 2 ions, and they're not at all together. If we have a higher concentration, so say close to 2 molar, well, that little m isn't molar. We'll get into what that means next time. It's close enough to molar that we don't have to worry about what it actually means yet. But say if we have a high concentration of sodium chloride, what happens is some of these sodium chloride ions are kind of stick together a little bit. So we no longer have every single sodium and every single chloride apart in solution. Some of them are together. So they act as 1 particle rather than 2. So at a higher concentration of sodium chloride, the Van't Hoff factor is no longer 2, it's a little bit less than 2. Okay, it might be 1.9 or 1.8 or something like that. Okay, so a theoretical one is you just look at the molecule itself, you look at sodium chloride, You know it breaks up into 2 ions of sodium and chloride, so theoretically it's 2, but depending on the concentration, it could be less than 2. Now it's never going to be greater than 2 because sodium chloride can't break up into more than 2 ions, right? Okay, so I have a question. So the more concentration, the more pairs there are because it is harder to dissolve, mix. It's not really that it's harder to dissolve or mix, it's just that the concentration of sodium and chloride ions are high enough that there's a chance that some of them could sort of stick together temporarily. They're probably still sticking together, falling apart, sticking together, falling apart, but they're not always apart as they would be in the low concentration situation. Okay, so it's not like that. Those circled sodium chlorides are always going to stay together. They will separate, but then there'll be a couple others that will, find each other and bond together for a, whatever fraction of a second or however long it's going to be, and then they'll dissociate and then reassociate and dissociate. So overall, we don't have completely separate sodium and chloride ions. We have situations where some of them are sort of stuck together for a short period of time. Okay, so all you have to know, basically, look at sodium chloride or any other ionic compound, be able to determine what the theoretical Van Hoff factor is. You never have to know what the actual Van Hoff factor is because there's no way for you to know. I would have to say, oh, the Van Hoff factor or the theoretical Van Hoff factor is 2, but actually it's 1.8 or something. I'd have to give you another number if it wasn't the theoretical one. So another question, the 1.9 in the graph is concentration, right? Yes. The little m actually stands for molality, which is a different way of calculating concentration, but we're not going to get that until the next section. So what determines what a high concentration is? That's a good question. I'm not sure there's an actual cutoff, and it probably is slightly different for each compound. So you don't have to worry about what high means. If I don't think there's anything in any worksheet or question, but if it is stated somewhere that, if the assuming a concentration of the solute is high, what could or would the Van Hoff factor be? All I would really be looking for is something less than the theoretical, or just to say, well, it wouldn't be 2, it would be a little bit less than 2, and that would depend on concentration or something. But I don't think I have any questions like that. So I don't think there's a hard cutoff for what high concentration means. Yeah, so the Van Hoff factor can't be more than 2. That's correct, because the most it could ever be for sodium chloride is 2. Okay, so I guess I would qualify that. It can't be higher than 2 for sodium chloride, right? For calcium chloride, it can't be larger than 3. And that is because when the ions break up, like sodium chloride breaks up into 2 ions. So they can't break up into more than that. So it can never be bigger than the theoretical value. It could only be a little bit less. Okay, so I'll go to the next slide. It just shows a little graph of some theoretical versus actual or measured Van Hoff factors, and this is given a concentration of 0.1 molar. So this is a lot less concentrated, molality. This is not the 1.9 that we saw in the previous slide. So in this case, 1.1 molar was high enough to provide a Van Hoff factor that was less than theoretical. Right, so you can see some of them are 4, some are 3, some are 2. Right, but the measured one is always less than the theoretical. And then we have something on the end like ethanol. Right, so this guy does not break up in water because it's not ionic. So that the theoretical and the measured will always be the same for a non-ionic compound. Right, one ethanol molecule in doesn't break up, so it's going to stay at 1. The only ones that can change between theoretical and measured are the ones that are greater than 1. So if you have an ionic compound like sodium chloride, magnesium sulfate, calcium chloride, or anything else that's shown on this slide, or any other ionic compound, so things that can break up in water. All right, so let's just do a quick thing here. So how about in the chat, just ask if you can answer all 3 of these. So Van Hoff factor for KBr, methanol, and sodium sulfate. What do you think? 2 for the first one. 3 for the second. These are just what's in the chat right now, not necessarily the right answers. We'll say the first one is correct, because the first one, this will go to K plus and Br minus. Okay. No idea what the third one is. All right. 2 for the third. 2 for the third isn't correct, and 3 for the second isn't correct. Okay, so the second one is really close. So if you look at the structure, CH3OH, if you go back to this slide, it's pretty close to this guy, right? The only difference is this one has a CH2 in it, so it's a little bit longer. So one is ethanol, one is methanol. Neither of those are ionic, right? Because to be ionic, you pretty much have to have a metal and a non-metal bonded together, right? Like calcium chloride, potassium bromide, that kind of thing. So nothing in methanol is a metal. So does that change your answer? Anybody want to guess number 2 now? 1 is correct. So this one is 1. This one is 2. And now the third one should be 3. 3 is correct. Now that one may be a little bit more difficult just because it contains something called a complex ion. And that, I'm pretty sure, is something you probably learned in General Chemistry 1. So the complex ion in this one is this, SO4. So that doesn't break apart on its own. That is one ion itself. So when sodium sulfate breaks up, it goes to 2 sodiums and 1 SO4, 2 minus. Okay, so other examples of some complex ions are CO3, 2 minus. Let me see. Oh, there are more. Oh, there's another one, PO4, 3 minus. Those are the only ones I can think of right now. But those themselves are ions, not like a single element with a charge on it, but it's a molecule with a charge on it. Okay, so learn to recognize those. If you're not quite sure what a complex ion is, maybe just take a quick look back in your textbook to see what those are. All right. So just a little quick thing on reverse osmosis. So if we know osmosis goes from, oh, hold on. Can you explain the second one? Sure. So the second one is it's not an ionic compound. So basically it doesn't break up in solution. If I were to draw it out, let me draw a structure. So it looks like this. If you were to draw a Lewis structure of it. Okay, so those are all covalent bonds. Carbons and hydrogens, they never break apart, at least when we're talking about water. If you get into organic chemistry, it's a whole different situation. But for us, carbons and hydrogens never break apart. Carbons and oxygens don't break apart. And until we get to talking about what an acid and a base is, this isn't going to, the OH isn't going to break up either. But later on, not for this particular molecule, but for other molecules, that OH could break up, but not for methanol. It just doesn't work that way. Okay, so if it has like carbons and hydrogens and oxygens in there, it's just not going to break up into different ions. Okay, so it's just it looks like that in solution, it looks like that out of solution. Okay, whereas the other two break up into different ions, right? So the methanol, the second one, since it doesn't break up, the Van Hoff factor is just going to be 1. All right. Okay, so reverse osmosis is just the opposite of osmosis. So if in osmosis, the water is moving from low solute to high solute, in reverse osmosis, it's the opposite way. It's moving from high solute to low solute. And if osmosis is a spontaneous process, then reverse osmosis is not a spontaneous process. So energy needs to be added to this system in order to make reverse osmosis work. So if you think of osmosis and osmotic pressure, right, we sort of learned that there's a natural pressure that is exerted on a system when osmosis is happening, right? So just let me go back to a slide just quickly here. Where am I? Right, so here. So remember when we were talking about this part, this difference here, right? So there's a pressure that is pushing up this way. And the osmotic pressure is just what do we need to do to stop that pressure from happening? So how much pressure is required to stop it is what osmotic pressure is. Now, if we want reverse osmosis, if we look at this, I'm just going to use this guy in the right here. So instead of having, so let's just say we started with this situation where we have a higher seawater, higher salt concentration, or a higher level on the seawater side than there is in the salt water side. So just ignore these balanced arrows. So for reverse osmosis, what we would have to do is exert pressure right here. We would have to push that down, force the solution to go this way back into the saltwater solution. Okay, so it's the opposite of a spontaneous process. We would have to actually push on that and force the water to go the other way. Right? And the greater the difference in those concentrations, the greater the pressure we would have to exert to push that water back through. Now, what if on this side here, what if that was just pure water? Okay, so what we would basically be doing here is doing a desalinization process, right? Or purifying water, removing salt from water if we're doing reverse osmosis. We have ocean water on the left-hand side. We want to make some drinking water. We do some reverse osmosis. We push that salt water or the seawater through a semi-permeable membrane. And then the other end, since only water can flow through that semi-permeable membrane, we end up with pure water on the other side. So using reverse osmosis is a way to convert seawater or convert ocean water into drinking water. But the main problem with it is it takes a lot of energy to do, right? There's tons of ocean water. There are desalinization plants. Some cities do use them, some cities near oceans do this kind of thing, but it's not exactly a cheap process just because it takes a lot of energy to overcome that osmotic pressure and actually reverse it. Okay, so this is something that can be done. It's not something that every town or city can do that lives by an ocean. Okay. So I know I'm taking longer than I wanted to because it's almost technically the end of our time in class here, but I think I just have one more thing here to do. I actually got a couple more things. All right. So using osmotic pressure to determine molar mass. So if you have some unknown compound, you don't know what it is, you can use osmotic pressure to figure out what the molar mass is. Okay, hold on, I got a question. So osmotic pressure isn't the pressure of the water, it's the pressure it would take to stop the water from moving according to that's the technical definition of osmotic pressure, how much pressure it would take to stop it. Right, so if you wanted to, let me go back again to this little diagram here. If you wanted to stop, so this is our starting situation where we have equal amounts of solution on both sides. If you wanted to stop this from moving up, you would have to exert the pressure equal to a pressure that is forcing it to move, right? So the osmotic pressure being how much you have to push down in order to stop that liquid from moving up. All right. Let me go back here again. All right, everybody good? I feel like you guys are asking more questions now that you don't really have to speak out in class, which is fine. Okay, so we can determine the molar mass of small samples using osmotic pressure. So basically all it is this whole part in here. Oops, that just means I got an email. Let me just turn that off. I thought I did already. All right. Okay. So this part here, this sort of working out of the equation. It's basically just saying you take the osmotic pressure equation, you rearrange it so you're solving for molarity, right? And that's basically going to give you moles per liter. And if you remember, molar mass is grams per mole. So by giving yourselves moles per liter, you're on the right track because you've at least got moles in there, right? You've got moles as part of your equation. If you know the volume of your solution, then you can just multiply molarity by the volume of the solution. That ends up giving you only moles. And then you'd have to have some kind of information about, well, how many grams of that solute was put or did you use to determine that osmotic pressure? And then we just figure out what our grams per mole is. Okay, so I do have an example, so we can just go through this quickly for doing this. And I will just say one thing. I think this is the one. I'm not sure how many of you downloaded these slides before this morning. As I was going through them, I realized that some of the questions I'm asking were not for this half of the chapter. They're actually supposed to be in the next half of the chapter. But some of the slides were from a previous textbook, and the things were just a little bit in different order. So if you don't have this question, either you can write it down or you can just download the newer version of the slides, which are on Canvas. And there's also a question that was removed from the slides, I think, too, the previous slides that were up there prior to this morning. Okay, so we have given some information. We have a small sample of a non-electrolyte isolated from a tree. Sample dissolved in enough water to make 2.5 milliliters. And the osmotic pressure of the solution is given at 25 degrees Celsius. What is the molar mass of the compound? Okay, so if anybody doesn't have this question, is writing it down, just give me a thumbs up right now. Otherwise, I'm going to change to a whiteboard, which will make this question kind of disappear. All right. Maybe I can do something. Let me see this if I can just copy it.
I look at me like that.
Because I was asleep at school.
No, you wasn't.
How you gonna try to tell me? We had a strike today.
I look at me like that.
Because I just woke up.
Those of you that are talking, I can hear you, just FYI.
Nobody's being holding.
Okay, here's the question. I got it on my whiteboard here. Okay, so we know we're given, we have osmotic pressure in the question, so we know we're going to have to use this, right? Our equation, IMRT. Who could tell me what I is going to be in this case? Is there a clue in the question to tell you what I is going to be?
Yes, there is. Since it's not an electrolyte, that means it's not going to dissolve into ions, so it should be just 1.
Correct. So you can either put it as 1 or you can just remove it because it doesn't really matter. So I'll just get rid of it just because it doesn't really matter anymore if it's 1. We're given molarity. Actually, we're not. We have to solve for molarity, right? So we have to rearrange that equation to be molarity equals pi over RT. Right, so we're given pi as 0.489 atmospheres. Our R is 0.08206. I don't have room for units, so I'm not going to put them. And temperature is going to be 25 plus 273, which ends up being 298 Kelvin. Okay, so from that, that's going to give us our molarity, which ends up being 2.00 times 10 to the minus 2. And I'm just going to write that down as moles per liter. Okay, so that's the first step, find out what molarity is. That's the concentration. So now the next step is we only need grams and we need moles for a molar mass, right? So what we need is molar mass equals grams per mole. So we have to get rid of liters in our molarity. So how are we going to do that? Right, if we notice we have a volume in the question, right? So if we multiply it by 2.5 milliliters, one way we can do that, you can either move the decimal or you can replace the milli with times 10 to the minus 3, because that means the same thing. So 2.50 times 10 to the minus 3 liters. So now our liters cancel out. And then that's going to give us the moles of our non-electrolyte. And
I
that,
don't know. Who's the last we only had one so far, and you know Dan, he was my partner, so we literally sat and then we got it done in like 30 minutes. The first one was so easy, but so far so good. Why is he not
I
talking
can hear
to me?
somebody talking. It's fine. I don't know how you can do that without talking to everybody. But anyway, okay, there's our moles, right? So now if we have moles, what is, how do you think we figure out our molar mass from moles here right now? What is the next step?
We convert the 47 milligrams to grams, then divide that by our moles.
47 milligrams. To turn that to grams again, milli is the same as 10 to the minus 3. So that's 10 to the minus 3 grams. Divide that by 5 times 10 to the minus 5 moles. I know my sig figs aren't right here, but that we'll just pretend I'm doing it right. And then we end up with 940 grams per mole. Okay. So again, we just do molarity first, get us our moles per liter, cancel out liters, so we only have moles, and then we're given a mass of our sample in the question. So that's our grams, divide that by moles, get us our molar mass. All right, are we good? I don't think I have too much more, at least I hope I don't. Okay, oh shoot, vapor pressure. Okay, I got a few more slides here. Okay, so now we're going to go into something a little bit different. So we're done with osmotic pressure. We'll go into vapor pressure. And so vapor pressure is, it's the pressure of a gas exerted by a gas at equilibrium with its liquid. So if we have the situation here, shown in the picture, we have some water, it's a closed system, and there's going to be some water vapor above that liquid. So what we have is a situation where we have some of the liquid water is evaporating into the gas phase, and some of the gas phase water is being condensed back into the liquid phase. So that's the equilibrium that this means. So the same amount of water is being evaporated as is being condensed. And the pressure that is exerting, if you were to measure that pressure, by putting some kind of a measuring apparatus there to measure that pressure, that's the vapor pressure of, if that was water, it would be of water. Now, if you have something like acetone or ethanol or other compounds that evaporate more easily, gasoline, for example, they would have a higher vapor pressure because they have more molecules of more of those molecules will be evaporating and present in the gas phase. Okay, so they're said to be volatile if they have a high vapor pressure. Okay, so vapor pressure increases with increasing temperature. So that probably makes sense, right? So if you have cold water versus hot water, there's going to be more water in the vapor phase if it's hotter than it is if it's cooler. And if there's more water in the vapor phase, it's going to have a higher vapor pressure. But the thing is, it's not a linear transformation. So it's, as the temperature increases, it doesn't linearly increase the pressure. If people are leaving, I'm sorry if you have other classes coming up. I think I only have a couple of slides here. Okay, so just a couple things about this graph here. This line here represents the normal boiling point, and that basically just means the boiling point at atmospheric pressure. So once a solution is heated up to a point where the vapor pressure is equal to atmospheric pressure, that's when boiling happens. Okay, and above and beyond that is, if it gets higher than that, then it's clearly it's just hotter, it's boiling more, I guess you could say. But once it reaches atmospheric pressure, once vapor pressure reaches atmospheric pressure, that means that whatever solution you're looking at or whatever compound, that means it's boiling, whatever liquid. Okay, so you can see in this graph that, okay, if we have temperature at the bottom and then vapor pressure on the y-axis, as the temperature increases, the vapor pressure increases, but the amount that the vapor pressure increases, or is going to be dependent on what molecule it is. So you can see something like, water here, right? So it should be at 100 degrees Celsius is when it's, right? So there's 100 degrees Celsius. That's when it starts to boil. But this guy over here gets to about 200 degrees Celsius before it starts to boil. And this one on the very other, the left-hand side, boils at somewhere around 30, I don't know, 30, what's that, 34.6. Okay. So does anybody have any idea why these compounds are boiling at different temperatures, or what property of these molecules is preventing them from, say, all boiling at the same time? Why are they different?
Intermolecular forces.
Intermolecular forces, right? So the first one, right, it's maybe slightly polar because of that oxygen, but not really. So we can probably consider that mostly non-polar. The second one has an OH, but just one of them, so it's got some hydrogen bonding. Water has a couple places where it can do some hydrogen bonding. This guy here has also 2 hydrogen bonds, plus a little bit of dispersion forces that can happen in there. Okay, so the stronger the intermolecular forces, the more energy it takes for it to boil, which means a higher temperature. Okay, so I think the last couple of slides here. So since that temperature pressure relationship isn't linear, if we want to make it linear and do some kind of predictions about, what vapor pressure a particular compound would have at a certain temperature, we have to apply a slightly different calculation. And this is done, the name of this equation is on the next slide. It's called the Clausius-Clapeyron equation. And so question, so more intermolecular forces means less vapor pressure. That's correct. Yeah, so the stronger they are, the less vapor pressure there would be at a specific temperature, right? So if you had 2 compounds at, say, 100 degrees Celsius, then the one that has the stronger intermolecular forces would have the lowest vapor pressure at that temperature. Okay, so this particular equation, the nice thing about it, it looks maybe slightly complicated, but as you will see with this equation and other equations that we do get into later on in the semester, it is in the form of a straight line. So, it's in the form of y equals mx plus b. So this is y, this is m, so m is your slope, this is x, and c is just a constant that we don't really have to worry about. Okay, so if we know what y is, and we know what x is, that's what's going to be on our axes. So there's our x, 1 over t, there's our y, natural log of pressure. Okay, so if we plot, so what we would do if we, just quickly, I guess, if we were to do this experiment, we would be measuring pressure at specific temperatures. So if I were to make a table here, whatever pressures we have, we would measure those pressures at different temperatures. So we would control the temperature and then measure what that pressure was. But in order to fit it to this equation, we would need 2 more parts of this table. We would have to have the natural log of pressure and then 1 over temperature, right? So we take the natural log of this column here, and then the inverse of temperature to populate those 2 columns. And then from there, we plot this graph. And then we can use anywhere on this line, we can figure out, well, at whatever temperature, what's the pressure going to be? We just have to do, the math, take the inverse of the pressure and the natural log of that. Sorry, the inverse of the temperature, natural log of the pressure to figure out what it would be. So this is what we do graphically. We're not really going to be doing that too much in this class, at least not an exam. I can't ask you to do a graph on an exam because it will never be exact. So we'd use this form of the equation, which would be, if you're given 2 temperatures, then what would a pressure be, for example? So at temperature 1, here's the pressure. At temperature 2, determine what that pressure is. So again, we have our temperatures in Kelvin. We have the universal gas constant, but this particular one is not the same one as osmosis. So remember osmosis, we had liter atmospheres per mole Kelvin. Those units don't work with this equation because remember the units of this are joules per mole. So we need an R, or a constant, that is in joules per mole. So the R in this case is 8.314 joules per mole Kelvin. Okay, So it actually is the same R as the other one, as the 0.08206, just converted to different units. Okay, so what on an exam situation or homework or something, you have to know which one you're using. Is it the one with liters, atmospheres, or the ones with joules and moles? Okay, if you're looking at delta H's as joules, if you're looking at pressures, it's going to be the other one. Okay, so another question. So more intermolecular force equals higher temperature it will boil at. Yes, that is correct. Okay, so I think this is the last slide here. So just an example of how we would use the Clausius-Clapeyron equation. And you should all have this slide, I think. So I'm just going to go right to my whiteboard in a second here. So we got a compound. We're given, a lot of this stuff at the beginning doesn't matter too much. Okay, we're given a delta H. We're given 2 temperatures. And then for the Clausius-Clapeyron equation, we know what R is. So are we given? Okay, so the normal boiling point is at 99 Celsius, heat of vaporization, and the pressure. So, okay, let me see here. My notes. Okay, so the thing about this is doesn't give you a number for the normal. It doesn't give you a pressure. So you kind of have to know in this case, what does normal boiling point mean? Okay, so you can do it, I guess, in, the pressure unit that you choose doesn't really matter. But in this particular example, we're going to use 760 torr. That's the same as 1 atmosphere, which is about the same as 1 bar. Okay, but we're going to use torr for this particular example. So that's the pressure we're going to use as a normal boiling point. Let me just go back here if it's shown on this graph. Here, right, so we have our vapor pressure. This one here is actually in torr. Okay, so I'll just quickly do this calculation or example of how we might do this. So we have pressure, we have 2 temperatures, we have our delta H. Okay, so the first thing we probably have to do is realize that, okay, so our R, we'll write the R down first, or our constant we're going to use, 8.314 joules per mole Kelvin. So that's telling us that our delta H has to be in joules. It's given to us in kilojoules. So we're going to have to turn or convert 35.2 kilojoules per mole to joules per mole. And to do that, we can just multiply by, say, 1,000 joules per 1 kilojoule. So that's going to equal 3.52 times 10 to the 4 joules per mole. Right, so now we have the right delta H. The other thing we have to look at is the temperatures. We have 99 degrees Celsius and 25 degrees Celsius. Those have to be in Kelvin because, again, our constant here is in Kelvin. So 99 degrees Celsius, that's the same as 372 Kelvin, right? I'm just adding 273 to it. And then 25 degrees Celsius equals 298 Kelvin, right? Was there a question? I heard something. No? Okay. Okay, so now we have all the information we need. So now we just have our equation, natural log of pressure at temperature 1, sorry, temperature 2, divided by the vapor pressure at temperature 1 equals negative delta H over R, 1 over T2 minus 1 over T1. And we can put delta H vap if we want. Whoops. Okay. So now we can put in the numbers, natural log of, we're trying to figure what it is, figured out at temperature 2. So this is going to still be vapor pressure at temperature 2. The vapor pressure at temperature 1, we're saying is normal, so 760 torr. And that's going to equal minus 35.2 times 10 to the 4 joules per mole over 8.314 joules per mole Kelvin. Oops, hold on, mole Kelvin. And then multiply that by 1 over 298 minus 1 over 372. Okay, so we have a whole bunch of numbers on this side of the equation. So instead of trying to rearrange stuff just to solve right now for just PVAP at temperature 2, we can just evaluate the right-hand side of the equation. And if we do that, we end up with minus 2.826. And that's going to equal the natural log of, I'm just going to call it PVAP 2 over 760. Okay. And to get rid of natural logs, you have to do the inverse natural log of each side. Okay, so hold on, I got a question. So temperature 1 is the boiling point temperature. Temperature 2 is whatever else is listed after. So you got to match temperature 2 with pressure 2 and temperature 1 with pressure 1. Okay, so at 760, the temperature was 370 something. So we're trying to figure out what the vapor pressure is at 298 or at room temperature. Okay, so to get rid of the natural log, we do the inverse of it. So that's would end up just getting rid of the natural log on this side of the equation. So we have vapor pressure at T2 over 760 equals the inverse log is E to the minus 2.826. E to the minus 2.826 is 5.925 times 10 to the minus 2. And then if we multiply that by 760, solving for the pressure, we get a pressure of 45.0 torr. All right, so I'll open up for questions in just a minute, but I just want to explain how you can tell at least that this answer makes sense. So if at a high temperature, so our temperature of 99 degrees Celsius, our pressure was 760, you would expect that at a lower temperature, we should have a lower pressure, right? So if you ended up getting a higher temperature, you know what's wrong. If you end up with a lower temperature, a lower pressure at that lower temperature, then you know at least on the right track. Okay, I'm sorry this took so long. I guess there's a little bit extra at the beginning talking about the strike. But if anybody has any questions, please let me know. If you have any questions about the class, the strike, whatever, email me, whatever you got to do. So I'll be here until everybody decides to leave, but I have nothing else for right now. You're welcome, Jack. What do you do with the worksheet? Do it if you want. It's optional at this point. If you want to hand it in, you can. I'll give you a grade for it. If you don't want to hand it in, what you'll see is EX on Canvas for excused, so it will not count against you.
I just got one quick question.
Yep.
So for slide 14.
Okay, let me get there. 14, this one?
Okay, so yeah, so for slide 14, so our formula was moles equal to pi times I times R times T, right?
Yeah, I'll just go back to this. Sure. Yep.
Yeah. So where did you get the 2.00 times 10 to the negative 2?
That is after doing the calculation here. That's after doing this. That's solving for molarity. So 0.489 divided by 0.08206 times 298.
Okay, and then you decided not to add the I because it's just one, right?
Right. Make sense?
Yeah, okay. And then the 250, 2.50 milliliters.
This guy right here.
Yeah.
Yeah.
So why is
came-
that 10 to the negative third?
Well, it's the same. It's the same as this, right? You could write it as same as 2.5 milliliters. You could write it as 0.0025 liters.
Oh, you have it in liters. Okay. So
yeah, it's in
you-
liters. Yeah.
Oh, okay.
Mhm.
Okay. And then that gave you your answer of 5.5 times 10 to the negative. Oh, that's only the mole.
Right. Because we've canceled out liters, we only have moles left over.
And then the 47 times 10 to the negative third in grams. Where did you get that one from?
That's from the 47 milligrams. Right. That's from right up top there.
Oh, okay.
Right. So that's the same as 0.047 grams.
Okay. Divided by the moles that we figured out.
Mhm.
Which gives, okay.
Yeah. If you're not comfortable using the 10 to the minus 3 like I did, you can write the 47 milligrams, 2.50 milliliters.
Okay.
As decimals.